everyone. Today we're going to be going over Newman projections, how to draw them, and then some applications of Newman projections. Newman projections, quite simply, are just simplified way of drawing alkanes, alkynes, any type of hydrocarbon. It just helps us visualize energy potential in a more simplified way than really looking at the molecule and being, okay, well, that carbon's going that way, that carbon's going that way, okay, there's a lot of torsional strain. We put it in a simplified format, so it's just, you see it and you just know. So let's look at this molecule here. I made a hypothetical molecule. It's a 2-carbon molecule, and it has substituents of X, Y, and Z, made up elements. How do we draw Newman projections? Well, we start with a circle. What a beautiful circle. Anyways, what we're going to do is first draw this carbon on the left side here. First, you have to kind of look at it as if you're looking down a carbon. Usually, you'll be given a perspective to look down and asked to draw a Newman projection. So here, we're looking down this carbon right here. That's what this symbolizes. And if we're looking down, we know that element X is bonded upwards and not coming in or out of the page as indicated by the wedge or the dash. The wedge here for element Z, right, that's coming out of the page, and if we look at it from the viewer's point of view, we're looking down that bond, that really just means it's going to the right of where that person's looking, right? So we're going to draw it to the right. So this would be element Z. And the opposites for this, it's down, but if we look at the viewer's perspective, it's going to the left. So we draw it to the left. So X, Z, Y, that's the first carbon. Now how do we draw the back carbon? Well, that's quite simple. We know that X is going down in this case, so element X is going down. We don't intersect the circle as to indicate or just kind of show that, okay, this carbon's behind, it's implied. Now if we look at Y and Z, instead of being down, now they're up, right? So they're going to shoot out this way. But which one is which? Well, we know that Z is coming towards the page, right? So if we're looking from the viewer, it's coming to the right. So element Z goes there. Element Y, right? That's a dash. That means it's going away from the page. So if we're looking this way, it's going that way. But if we look from the viewer, it's going to the left, right? So we just draw it to the left. So that's a Newman projection. Pretty simple, right? Just try not to get confused. Just understand kind of how the wedges and the dashes work, right? And then single bonds, they're in the page, so you know they're quite easy. And now for the energy part and why we draw Newman projections. You know, it's one thing to do something, but you need to know the why behind it. Well, with Newman projections, as you can see here, we have different conformations, right? The one we just drew is staggered. There's also eclipsed. What does that mean? Well, there's a thing known as torsional strain for molecules, right? A lot of torsional strain isn't very stable, right? But we know that if it's staggered and we decrease the torsional strain, right? We increase the dihedral angle. That's some vocab that you gotta learn. Dihedral angle is the angle between any given atom around this Newman projection, right? So yeah, we're gonna, so at 60 degrees, right? We have the least amount of torsional strain. There's not a lot of overlap, right? So this is favorable, this is stable. And we have eclipsed, that's our second type of Newman projection. There's other ones like gosh and all that. But we won't get into that in this video. This is a very simplified introductory video to Newman projections, but we have the eclipsed, right? So what is the eclipsed? Well, think about it like this. It's like right on top of each other, right? So there's a lot of torsional strain in this molecule. So this is not really stable. This is not really what we would want from molecules. We want something more like that to be stable, right? You can even relate this to ideas of like entropy and favorability, right? That kind of thing. So just keep that in your mind while you work through this. So just to visualize more of kind of what's going on. Here's energy graphed as a function of the dihedral angle, right, that of each Newman projection. So we have a lot of energy starting, but why is that? Because the dihedral angle is 0. There is no difference between, it is fully eclipsed, these two H's, right, fully eclipsed. The H's are like this, right, and they're having a lot of torsional strain. They do not like it, so it's very high in energy. But as we increase the dihedral angle, right, and we kind of separate it as far away as we can from each other, those two hydrogens that I've drawn out, well, then the energy goes down. The potential energy of that molecule goes way down, right, because it has almost no torsional strain on it. But let's say we now eclipse the hydrogen and this atom here while we rotate. We're getting there, and you'll see that now other hydrogens are eclipsing, right? So the torsional strain is still up, right? So that's quite simple. Well, there's more complex ways to it, especially if you have different substituents of different masses. That will cause differences in energy, all right? So have a look at that, look online, stay curious, enjoy learning. It's quite fun. Thanks for watching, guys. Goodbye.